Well, we are again extremely fortunate to have an incredibly accomplished engineer from Northeastern's own faculty as our guest today. Ahmed Busnaina, PhD, is a distinguished university professor, the William Lincoln Smith Chair Professor, and the founding director of the National Science Foundation's Nanoscale Science and Engineering Center for High-Rate Nano Manufacturing, and the NSF Center for Nano and Micro Contamination Control at Northeastern University. Prior to joining Northeastern, he was a professor and director of the Micro Contamination Control Lab at Clarkson University from 1983 to 2000. Dr. Busnaina is internationally recognized for his work on nano and micro-scale defects, mitigation, and removal in semiconductor fabrication. He specializes in directed assembly of nano elements and in the nano manufacturing of micro and nanoscale devices. He developed many techniques for directed assembly and nanomaterials-based manufacturing of nanoscale structures for energy, electronics, biomedical, and materials applications. His research support exceeds $47 million. Professor Busnaina has authored more than 600 papers in journals, proceedings, and conferences, and he has organized and chaired more than 175 conferences, workshops, sessions, and panels for many professional societies. We are having an incredibly extraordinary level of guests in this class. Please join me in welcoming Ahmed Busnaina. Thank you very much.
Good morning. Thank you very much, George. Today I will talk about things that, new technologies, that probably you've seen and heard about it, but you probably do not realize how valuable it will be in the next few years. So the title here says, The Future of 3D and Electronic Printing. How many of you heard about 3D printing? How many of you heard about electronic printing? Just very few. So they're basically the same. Both of them use inkjet type printing or a stencil or screen printing. But one basically makes 3D objects that are usually just an object that's not functional in any way unless you put it as part of another system. The other one is printing of devices, display, electronics, complete electronic systems. And right now they're just used for either making objects or making a 3D printing system. So I'm going to talk about a new technology that brings these two together and make new things that could revolutionize the manufacturing as we know it today. And the applications are actually not just for electronics, but for energy, for sensors, for composite materials, for medical applications, a variety of things. But before I go into the topic, let me just show you that this is not just my work. I'm only part of this work. But this is a center that is funded by the National Science Foundation, and it is focused on creating a new technology for nanoscale manufacturing. And Northeastern is the lead university, but also it has UMass Lowell, has University of New Hampshire, and Michigan State University. And as you can see, there are more than 30 professors involved, about 20 postdocs, more than 100 students between graduates and undergraduates. And also we work a lot with industry, so this is just one slide, shows a lot of companies that we work with, but the message you get from that is that how diverse these companies are. So you see aerospace, you see electronics companies, you see equipment companies, or cementation companies, you see polymer companies, you see oil equipment companies, the variety of things, variety of companies that have many different applications, and that means that this manufacturing technology can be used for a variety of applications, which is very useful. It's not just for electronics, for example. So how do we start on this path? Well, when we started, goes back, I'm not sure how many of you are up on the latest nanotechnology field or how it even started, but it started with an initiative by the US government in 1999, and it was called the National Nanotechnology Initiative, and it was President Clinton started it, and it's been on for about 15 years now, and the funding is half a billion a year going on. And so a lot of investment happened, a lot of people worked on it, thousands of people. But, and when it first came out, we heard about all these promising technology, how these nanotubes are stronger than steel, more conductive than copper, how these quantum dots you can use them to store information, and the information will be there 100 years later, unlike the flash drive that your information can be lost in 3 years or so, for example. And we heard about all these wonderful things you can do with nanotechnology, treatment of cancer and all that stuff. But 15 years later, we don't really see many applications. Nothing that you actually buy today as a consumer has much. And if it has, it's mostly used as a bulk material to strengthen, let's say, a part of a car or a part of an airplane and so forth. And yet, the electronics that we use today, your laptop, your phone, don't really use any nanomaterials at all. And what they use is they use a technology that started in the 50s and 60s and saw a big leap in scaling down to the nanoscale in the late 80s and 90s and 2000. But the fabrication facilities are so expensive. For example, it's about each fabrication facility will cost about 7 to 10 billion. One facility. There's one that was just built in Albany, for example, about 2 years ago, and it cost 7 billion. They're building another one, cost 10 billion. And it's so expensive that only about 4 companies in the whole world that actually can afford to build facilities now. And these facilities use a huge amount of power and a huge amount of water. And so the question that people always ask, well, why didn't these companies, knowing that this new nanomaterials give them a huge advantage in performance and in capabilities, why did they use them? What was the problem? And the problem is that it didn't really fit any of the manufacturing technology that they use today. The manufacturing technology that they use today is they start with a silicon wafer, for example. This applies to all the chips you have in your phones and your laptops and even in your car. They start with a silicon wafer, and then they deposit the material, then they etch, and then deposit the material, then they etch back, then deposit the material. And it's about 300 to 400 steps. And each step is very, very complicated. And so when you give them nanomaterials, nanoparticles, nanotubes, and so forth, they have no idea how to deal with that. They don't know how to make structures out of these. They don't know how to make a circuit out of that. They have no idea. And so the question that we dealt with, and a lot of people who work in nanotechnology, well, how can we actually develop a technology that will actually enable them to do that? Do we need a new technology? Well, the answer is no. We don't really need a new technology. We can use the technology that's already there. And that technology is printing, okay? Because basically these nanomaterials can be put in a solvent or in water, and they'll give you an ink. And you can print with that ink, pretty much like the 3D printing that we talked about. And actually you have products, you've seen the Kindle, that's actually printed. A lot of the sensors that we use are printed. Your antenna in your phone, all the RFID tags are printed, for example, because it's a lot cheaper than actually doing it the traditional way by using a silicon manufacturing based. And so flexible displays, so now they make a TV that you can actually fold and like a poster, you put it up on the wall, for example. Actually, they have that. It's not available for consumers yet, but it's actually there, and you can make it up to 50-inch, 60-inch screen. And a lot of the low-end electronics, which means not the high-performance electronics, not the flash memory, not the processors, but a lot of the slower one actually are printed. So problem solved. Well, not really, because even though these things are very capable, the problem is that they don't really compete with the high-end electronics, because the high-end electronics, the components, the wires, the line width of the smallest wires is about 20 nanometers, for example, and the smallest these printing technology that exists today can do is 1,000 times larger. Okay, it's about 20,000 or 30,000 nanometers. That's the smallest they can go. And also they're very slow. Have you seen an inkjet printer? It goes line by line, so it's very, very slow. So if you make a very dense structure, make it very small, it doesn't work. But even with these limitations that they're 1,000 times larger, they're very slow, even with these limitations, they're typically about 1/10 or 1/100th the cost of the electronics that are made today using the silicon and the traditional manufacturing way. So even with these limitations, they're still much cheaper. 1/10 for a simple device, and for a more complicated device is 1% of the cost. So I mean, I just told you about electronic printing, and you probably don't know how big the market is. Let me just give you an idea about how big the market is. So electronic printing market is about $50 billion this year. 50 billion, okay? And it's projected to be about close to 300 billion in 10 years. Now, this is using the old technology, which is limited to about 20,000 nanometers, smallest dimension they can make, smallest wire they can make, for example. And the products are expanding, the application. If you can print it, why should I go etching with vacuum and all that stuff? This is just printing in a room temperature, room pressure, for example. It's very cheap. But, like I said, to make this technology actually get to make things like this, or like your laptop, it has to go to the nanoscale. And that's the challenge. And so far, there's no, the options are not there. They're in the research stage, and they're not really very good options yet that has been commercialized. So, but the challenge is that we said, okay, we can make, we worked on many technologies that lead to printing, but to make that happen, what do we have to do? Can we just make nanoscale printing and be successful? Is that enough? Well, actually, if you want to make a product and you commercialize, that's not enough. So the nanoscale, making the nanoscale using digital insertion technology is not enough. You have to do two more things. Whatever technology you make, it has to be much, much faster than current technology. Orders of magnitude faster, because that current technology is extremely slow. Second, it still has to cost the same or lower than current technology. That's how you be successful. So you match a price or beat it, and you have to be way faster than what's being done today. And imagine if that happens, okay? You will make nanoscale manufacturing affordable and accessible. What you're doing is you level the playing field. You democratize the technology. You no longer have to have a $10 billion to build a fabrication facility. You no longer have to go to a company that has a $10 billion facility and pay him hundreds of thousands of dollars to just make a few chips. You don't have to do that anymore. And so you can just buy one of these tools or go to a fabrication facility that's cost maybe 20 million or 30 million at the most and make your product. And what that will do, the impact of that is not just about electronics, because you can do a lot of different things with this technology, but that will open the door to a lot of innovators. And people are smart. They can think of a lot of products. And if you give them the capability to do things very small and very fast, they come up with products that no one has thought of yet. But also, the people who want to make the typical product that you buy today will have a huge advantage, because they can make the product at 1% of cost of the current cost of manufacturing it. So that gets us into what the technology is. So basically, we have a lot of technology developed. I'll explain how it works. But it uses directed assembly. That means chemistry at the microscale or nanoscale, and put that into a printing system. And the ink is made of nanoparticles, nanotubes. So you can have insulators, you can have conductors, you can have semiconductors, you can have a variety of things, and use what we call template printing. And the particles be attracted to the template using directed assembly. I'll show you that using an animation. So this is actually what the system looks like. This is what the template looks like. And using the technology and having the technology embodied into a fully automated system to print was just actually, the tool was just delivered about 3 days ago. And we're still going through the software and so forth. And it's fully automated. You just have to put the recipe and it takes on. And this tool basically is 1,000 times faster printing than current electronic printing. And the structures we can print is 1,000 times smaller than current technology. So it is basically, this is just the first step toward actually making nanoscale printing affordable, for a lot of small companies and even large companies or medium-sized companies. So the question is, how does it work? Well, you start with a template. This template has embedded nanowires that represent whatever circuit, pattern, whatever structure you want. Then you immerse that into a solution that has the carbon nanotube or nanoparticles, whatever the nanobuilding blocks that you need to build the structure from or a circuit from. And then you have a counter electrode. You pass a current that's about 2 volts. And then the particles or the nanotubes will they have a negative charge, so they migrate to the template, and they assemble exactly where you need them, only where you need them, where you want them to assemble. And then the process takes about 90 seconds or so. You're done. You take it out, and then you transfer it over whatever you assembled to another substrate, and then the template goes back and takes another material or the same material, or you take another template that represents a second layer, for example, and you do it, and it's repeatable. And you can use the templates thousands of times. So each layer of circuit will have a template, for example. Or you can have, sometimes you may have just one layer, for example. So you can do that. And so we've been talking about electronics and so forth, but actually it's not just electronics. It's a variety of products. You can do materials, you can do composite materials, you can do antennas, you can do shielding, you can do radar, you can do metamaterials where you manipulate the transmission or the scattering of light, for example, like making a flat lens, for example. You can do batteries that will last, I'll talk about that a little bit more also. You can make energy harvesting that takes body heat or takes heat from any heat source and directly charge your battery, for example. You can make sensors, flexible electronics. You can make biosensors, drugs, and so forth. These are some of the examples that we're actually working on. Sensors that do early detection of cancer, for example. Band-Aid that you put on your hand and will read not only glucose, but urea, lactate, and any biomarker that is water-soluble that exists in the blood, for example. And that means you don't have to get to the blood. You can actually read whatever the body state is by having a Band-Aid that has contact with sweat. That's all you need. Drugs, for example. We can print drugs so that they can be taken orally. So that means you will never have to take an injection again, okay? Because a lot of the drugs have to be injected because they're not soluble. You can do flexible electronics. This phone, there's no need for this phone to be that hard. It could be made very soft, you can bend it and so forth. It's feasible. It's very feasible. You can make the flexible display, for example, a whole TV. Actually, there is a company now that makes a TV that you hang on the wall, and when it's not running, it's transparent. You can see a picture behind it. When it's on, it's on. Okay. You can watch TV, and then you turn it off. You can see the wallpaper or whatever's behind it. You can do lightweight, durable materials, for example, to replace metal in aircraft. You already heard about the Boeing 787. The Boeing 787 is made entirely of plastic and carbon. It's only 10% metal. Okay, so think about it. You're flying in a plastic airplane, but it's very durable. It's very reliable. You can make batteries. We're going to talk about batteries and so forth. Okay, so we talked about the printing process, and this is a summary of the animation that I showed you. And so what is the process? The process is additive. That means when you manufacture, you always do put material and take material, and put material and take material. Whether you're doing electronics or you're making something, you make a table. Take a piece of wood, you cut it, and you remove stuff, and you put it in. Well, the additive means you just add. You never take off anything, because you have the building blocks and you just add it. This is how nature builds things. It's all adding. It doesn't take anything out. The material you have, you use all the material you have. There's no waste. It's high throughput, like I mentioned. It's room temperature and pressure. So a lot of these manufacturing processes use vacuum and use very high temperature. There's no need for that here. You can print on polymer or on silicon or a hard or flexible substrate. It's material independent. You can use any material you want, organic or inorganic. It doesn't matter what the property is. Very low energy consumption, very low capital. What does the structure look like? So the top structures were made of nanoparticles. So the structure is about 50 nanometers in diameter, and it's about a few hundred nanometers high, but the building blocks was 2 or 3 nanometer particles. So you take them in, you assemble them, they fuse, and you got your structure. And you can do it over a large area, or you can do it as large as you want. Here, these are nanotubes. So nanotubes you can print on silicon, you can print on polymer, you can align them, you can build all kinds of things with them. Whether you're building circuits, you're building sensors, you're building composite structures for aircraft, anything. Polymers also, you can do 2D or 3D polymers using assembly. It's a very fast process, very straightforward. These are what the template looks like. I explained earlier. These are flexible templates, and this is hard template. So why do we have a flexible template and a hard template? Well, because when you transfer the process from a template to a substrate. Now, when you print, you have a gravure roller, or you have a plate, and the plate is hard, and you have paper which is a little bit softer. You can push it down. So when you print, you have to have full contact. So when you have two hard surfaces, you cannot have full contact. It's almost impossible. So to print on a soft surface like polymer, for example, we use a hard template. But to print on a hard surface like silicon or other surfaces or metal, you have to have a softer plastic-based template. So this is the plastic-based template. There are two of them. And this is the hard template. So silicon, tungsten, the conducting wires are tungsten. And this shows examples of the assembly before it's transferred from the template to the substrate. These are fluorescent silica particles, green fluorescent, to see them. These are silica fluorescent particles. These are silica red fluorescent particles. Okay, and you can also have a lot of other advantages like aligning the nanotubes. So when you align nanotubes, you get more properties. You get more conductance. You get more strength out of them if you're building a structure, for example. And the process actually can be much, much more in terms of the scale. So I showed you 15 nanometer scale. This is millimeter scale. This is 2 millimeter scale, 3 millimeter, 5 millimeter scale. So the process can do nano, micro, or macro, or all of them together in the same template. Okay? So when we first were talking to companies and to National Science Foundation, and we're talking to them, we want to make this manufacturing technology. This is a few years ago, before we got the funding. And they said, so you want to make new manufacturing technology? We said, yes. So they said, well, so what is your product? They said, well, our product would be manufacturing machines, tools. And they said, so what are you going to manufacture? I said, well, anything. They said, no, really, what are you going to manufacture? And so I said, well, we're building it so anybody could use it to come up with any idea. I said, well, okay, but how would you know that would work for them? They said, okay. I said, well, okay, I see where this is going. So we have actually to make a product. We have to think of a product and make a product. And so we had a team split from the group that will think of about making representative products. They may not be the best products you can make, but they will demonstrate the functionality and the capability. And so we came up with, for example, so I'll give you a few products, each one in areas. So electronics, for example, we made electronics products, for example, using new material that is not used in any electronics that you use today, carbon nanotubes, molybdenum disulfide, which is a semiconductor just like silicon, for example. You can make inverters, you can make transistors. You can make actually a transistor on a polymer that you can wrap around your finger. Circuit, a whole system. Okay? It's so thin that you can wrap it. You cannot tear it. It's very strong, but you can wrap it around your finger, like you can see that picture here, for example. So this one is probably 5 to 10 years ahead in time. But the biggest application that will catch on, and there's a huge need for it, is electronics, sensors, with its associated electronics. For example, so there's a huge need to make really sensors to go anywhere. And these sensors are not, we're not talking about listening to people or filming people. No, we're talking about sensors that will detect chemicals, whether it's in the air or in an oil well or in an enclosed structure anywhere. But these sensors have to be very fast, very cheap, very accurate, and very, very small. Okay? So these sensors we made for the oil industry, and these sensors have to withstand 200 degrees Celsius and have to withstand very, very high pressure. And you can see the sensor is really, really tiny. I mean, the sensor is very, very small here. It's about, the whole sensor is about a few hundred, it's about less than a millimeter, the whole sensor. And you can see here, the sensor with its chips and with its power and so forth should be about less than a millimeter. It's like a dust. And you throw it away, and actually you can collect information using, you can detect thiol, you can detect hydrogen sulfide, you can detect simple alkanes, methanes. So for those of you who are not chemists and don't know what these things are things that exist near oil, okay? So if I'm drilling for oil, for example, and I have water, if the sensor comes near the oil, I will detect these things. So I will know there's oil there. That's why they do that. But these sensors will be completely independent. You don't have to connect to read it. It will communicate to you through RFID tag, just like your phone, antenna, through a small antenna. So that's one technology that has a lot of need. And depending on what you want to detect, you can functionalize it with anything you want to detect. And you can detect a whole variety of things. And they have to be reusable, of course. This is another one that three of our students actually started a company called Biolome, and it's based on the printing technology that we developed. And this is a sensor that can detect cancer 6 months to a year before any technology can detect it now. And that means that you can actually, the treatment can work because you catch it at the very early stage, and you can treat it fully. And actually you can, you don't have to take a whole, right now when they do a blood test, they have to take a whole tube, for example, very large tube. This is like a glucose test. Very tiny droplet of water can detect cancer or cardiac markers very quickly. And they're working on an iPhone reader. So if somebody has cancer, history of cancer in the family, for example, and they're worried, they can just take a droplet of blood, put it on that small piece, and put it in an iPhone and actually read it. This is the sensor I told you about, which is the Band-Aid sensor. This sensor, so the idea started with the Air Force. The Air Force and for NASA also. They have a lot of people that are flying for a very long time, and they get tired. And typically when they asked to get tired, they say, no, I'm not tired, right? They can't admit they're tired. And so what they do is they have sensors in the helmet, in the cockpit, that will detect actually if their eyelids actually come down. So they go to this length actually to find out if the person is tired or falling asleep. So there is an easier way, and the combination of glucose, urea, and lactate tells you how tired the person is. And that means that you can put it in, it will measure it and communicate it to the commander. But for athletes and for hospitals, it's very, very important to detect that, especially for critical patients. So this is something that they're looking at. Energy storage, okay? So what we have done is we looked at batteries also. And with batteries, for example, when I bought this phone 2 years ago, it would last 14 hours, 15 hours, 20 hours. Now I'd be lucky if I got 6 hours out of it without charging it, okay? My laptop also was like 10 hours. Now it's like 4 hours, 5 hours, and then it's done. So why is that, okay? Have you thought about why is that? Why can't we get more life, and why the performance or the capacity deteriorates with time? Well, because the technology of making batteries has not changed for the last 30 years. All they do is if you take a battery, open it, all it has the cathode, which is aluminum, and and you bring the lithium salt that you work with, which is lithium iron phosphate, lithium manganese oxide, whatever it is, you mix it with carbon black, you mix it with a binder polymer like PVDF, and you press it and you put it on the aluminum foil that's your cathode. And then the anode would be copper with graphite on it. And then you put a membrane between them, you put the electrolyte, that's it. All the batteries you have are like that, okay? And so what the research has been going to make the chemistry, to change the lithium salt that you use, for example. So, and to make it high energy, to make it that, but they have not solved the problem with the life and so forth. And one of the problems with that is because if you think about it, the lithium particles that we have in the battery is where we store the charge and where we retrieve the charge. And so they're mixed with carbon black. And so to actually have, from the cathode to the anode, to actually have the charge, I have to hop from one particle, carbon particle, to the other, to the other, to the other, to get to it. And then I hop back. And so there isn't like there's a wire to connect you, okay? It's just random. And when you use the battery, it heats up and you have gaps and you have chemical reactions and so forth. And so as a result, the number of particles that you have access to will decrease and decrease until you lose 95% of your battery capacity. And so what we have done, we said, well, one of the ways to fix this is to make sure that everything is connected, right? So how do we connect it? So we have basically carbon nanotube, which are very conductive, which are very small, and have them in between the particles and in between the nanotubes, but also all the battery has to be layers, and all these layers are interconnected. So now I have access to all of the particles, or most of them, or 80% of the particles, all the time. No matter what happened, I still have access to them. And as a result, we can charge. So if you take your phone here, how long does it take to charge your phone? An hour? 2 hours? Right? Let's say 1 hour, okay? Now, do you know that you can actually charge it in 5 minutes? Well, you can. But if you do, you will only get 5% capacity left, or 10% capacity left. So we develop a battery that you can charge in 5 minutes, and you still have 95% capacity left. Okay? So technology exists. It's just that there has been no innovation of making the architecture of the battery. All the innovation was focused on the chemistry of the material that's used to store. Okay, the last couple of things. The energy harvesting. So when you say energy harvesting, most people think of photovoltaics, think of the sun. Well, actually, you don't have to have that. We can use a simple antenna, very similar to the antenna you use in your phone. And basically, this antenna can harvest electromagnetic waves, but in the thermal regime, in the infrared wave regime. And you need a diode, and from the diode, you go directly to your battery, and you can get up to 30% efficiency, which is pretty huge. Okay? Multifunctional structures. You can do antennas, you can do touch display. Do you know how your phone touch display works? How many people know when you touch this, how does this actually works? Do you know how you get the charge from your finger to the circuit to activate an app, for example? Do you know how that works? Well, actually, you will not find this published anywhere, by the way. But what it is, it's under this glass, there is a polymer, polyimide or PET, and this polymer has a grid of copper wires. And these copper wires are about 2 micron wide and about 100 micron spacing. And this grid basically is the one that you do it. And this is done by the old traditional way because they cannot print things as small as 2,000 nanometers. The smallest thing they can print is 20, which will actually not be transparent. You will actually you will not see through the apps. It has to be much smaller than 2 micron or 2 micron and smaller to actually see through it. So you can actually use it and see through it. So when we showed this to the company Foxconn that makes the iPhone for Apple, they said, oh, if we use printing, we can cut our cost for the current phones by a factor of 10. Because the way they do it is they deposit material using vacuum, physical vapor deposition, and then they pattern, they put photoresist, they pattern, and then they etch all the copper away, with the exception of these nanowires. So this technology, what this shows is a grid like the one I'm talking about, but this is made of nanotubes, and this shows the conductivity and the transmission. So in order for the touch screen to work, it has to be very well conductive, and you have to see 99% through it. Okay? So that's how this works. Okay? So the question now is, where do we go from here? Well, you can actually build a fabrication facility, not at 10 billion, but at 50 million or less. Okay? And we took the first step to do that, and we built a machine to do it because basically we're doing it in the lab. And this machine looks here, for example. The templates go here, the substrates goes here, This is the assembly station. This is the transfer station. Remember the animation? And this is the alignment. Why do we need alignment? Because when you do circuit, you print multi-layers, and these multi-layers have to communicate with each other. There are interconnects. And if you don't align them so that the interconnect between the layers are exactly on top of each other, it will not work. So you need to align them. So there are markers usually when you put the first layer, then there are markers, and the second layer, there are markers. You align them, and then once they're on top, you put them to each other and you transfer. And so that's, and this one is actually in the Burlington campus. It's already been installed, and the public demonstration will be Wednesday. So I have a lot of people from the Navy and NASA, Air Force, NSF, a lot of companies, Raytheon, Lockheed Martin, Samsung, all these companies are coming on, and unfortunately I cannot invite you because we're over capacity, but certainly after that, George can arrange if you want to come and see it, we'll be happy to show you. Okay, and that's it.
First of all, thank you very much for an incredible presentation. Actually, it's very credible. It's extremely credible. And we take the normal question period to a sort of greater extent here. First of all, it is fascinating for me to see how, and I imagine for most people here, to see the number of steps or the amount of depth of research and experimentation that lies behind something like the interface on your phone. But I wonder if you can, you laid an extremely good background for us, those of us who are not in this field, about the importance and the sort of transformational nature of nano manufacturing. Remind me again what it is that makes what had been such an expensive enterprise, what was the key development that made it possible to do this now at a much more affordable way?
That's a very good question. How many of you think that 3D printing just came out 2 or 3 years ago or 4 years ago? Did you know that 3D printing has been around for 20 plus years?
Wow.
And it used to be called rapid prototyping. Designers used to make it like when you're an architect, you make a maquette, right? So they used to use it. So why didn't anyone know about it? And how come it's all of a sudden became well known? Well, the reason is very simple, actually. It was known when the price for the printer went down from $100,000 to $3,000, and then down to $500. Then they came up with the 3D printing, which is very descriptive and very good name than rapid prototyping, which is describe what the product was, not what the process is. And so that's why, it's been around for a long time. So the printing has been around for a long time, and we print ink, on paper. And somebody says, well, why can't I print a circuit instead of using, these particles, these dye particles, for example, that give me a red color, an inkjet, for example, or a laser printer. Why don't I make copper particles or silicon particles to make the silicon to make the transistor, and copper to make that? And so that started a few years ago, actually, and most people don't even know about it, even though they use it in everyday's applications, for example. And so when we looked at that, we said, well, this is great, but how can we go into a smaller one so that we can compete with the current silicon-based, vacuum-based, high-temperature process? And initially, by the way, when we started the center, we didn't even call it printing. We call it directed assembly. And we focus on directed assembly that's taken these particles and actually assembling it in very structured, two-dimensional or one-dimensional structure or three-dimensional structure, and basically building something out of it. But as we talk to people and we try to explain what we're doing, most people won't get it. They don't get it. What is directed assembly? What do you mean, directed assembly? You're just putting something on top of something else. What is that? And how does it work? How can you get these particles and how you can make it go specific things? And then when you looked at it, we're saying, well, we use a template to make the assembly, and we transfer it. Well, that's exactly like what what the template printing that Gutenberg, the Bible, done. 700 years ago, right? 700? No, it's about 700, 1400 something.
Yeah, 600 maybe.
Yeah. So basically, we called it printing, and that was the time when 3D printing came out also. And it is printing because everybody gets it. You know, it's a technology that we worked on for a long time, like you said. It's how do you get these nanoparticles to go exactly where you want them and only where you want them, and then come off. You cannot do this with inkjet.
So was that and see, this is interesting, and especially within the context of kind of framing this as a let's say a problem-solving approach. Was it the ability? I love the little animation that made clear that just a little bit of an electrical charge gets you to be able to assemble elements.
Yes.
These little components that are in a fluid, as I understand.
That's right. In water, yeah.
And they connect only to the armature.
That's right.
And then the others. And then the others fall away, or
well, the others, we use technology that makes hydrophobic hydrophilic. So let me try to explain that. When your car is dirty, right, and you get a rain, you have big puddles, right, on the car hood and so forth. When you wax your car, what happens? Or when you use the rain dance, what they call it for your windshield, right, the water beads and falls off, right? Well, that's the same technology we use. So the areas that are the assembly is supposed to happen on don't have any of that wax, if you will.
I see.
And the other area will be wax, but it's very stronger than your typical wax, and it's very thin. It's about a nanometer thin, and it will last for 100 times, for example.
That's why the length of time between replacing the.
That's right. Yeah. So and it's very easy to you put it. It's a vapor thing. You expose it to that vapor, and it's functionalized, and it's done. So it's all about chemistry and engineering at the nanoscale, you know, and it's problem solving because you have a problem. How can I do this, and how can I do this in an inexpensive, in a simple way? You know, the simplest design, I mean, the best design is always the simplest design. But also, the best product is the one that you can make very cheaply. You know, if it's expensive, no one will buy it. You know, so as you design this, not just something a product, but you design even your process. You have to keep thinking about that. How can I design a process that is scalable? So if my process works in a very tiny area, if I have a large something like this, does it work the same way? Well, actually, if you know the fundamentals, that if you can manipulate the forces at the nanoscale or the microscale, if you can manipulate them over a small area and you can manipulate a large area, you can. But if you think by just making the tool small, large, or the substrate large, it will not work. It doesn't scale. So there's scalability, and there's speed, and cost. You know, all of them are tied together.
Well, I like very much that you were able to, in this very complex enterprise, you were able to tease out just now for us a very clear, specific problem to be solved, and that was simply around the substrate or the template. That is, we need to find a very precise, very specific way to separate things to which material will cling, and things from which it will fall.
That's right.
Now, see, that for the purposes of what we've been talking about thus far, and we'll continue to talk about in this course, that's a really incredibly straightforward and clear. Now, when you have a problem defined like that, then you can, let's say, if we just zoom in on just that issue, we say, okay, now what are the pluses and minuses of various slippery materials? Some of them might bleed onto the other material, and that wouldn't be good. So now you're establishing, for the purposes of our sort of cyclical way of working, a set of metrics that are very specific against which you can test.
That's right. Yeah, you have to do that.
And so you must, in your large group, I didn't realize when we started that this was there was a collaboration between 4 universities and 30-some professors and 160 people. We could have a whole management discussion about how that goes. That sounds like a really complicated enterprise to me. And maybe only architects are used to working with so many different people, with everybody solving maybe a different problem. But the need to parse any task that you guys take into incredibly small bits, is that how you work as a team? Do you break apart nanomanufacturing into its requisite components and have different groups work on different parts?
That's a good question, because we have large groups. We even have people who do philosophy You know, because there's ethical part of it. You know, nanomaterials sometimes can be toxic, sometimes can be harm the environment. So we have people look at the ethics of it. People look at the economics of it. So we have people from philosophy, from economics working. But basically we divide the center in about 4 different thrust areas. One is focuses on the nanomaterial, the nanobuilding blocks. How do you make them? How do you make them cheaper? How do you make them so they don't degrade? For example, organic electronics. We talk about silicon as semiconductor, but there's a lot of organic semiconductor that's a liquid that you can actually spin and as thin film, and actually will act where you can make transistors out of it. So, but the problem with most of these materials that you can buy today, if you expose them to light, they degrade. They're not good anymore. They become insulating. If you expose them to oxygen also. So some of our professors worked on making it robust, meaning that you can actually work with it in oxygen and light. And that means you don't need to work it in glove boxes, for example. So there's one guys that work on the nano building blocks. That's nanotubes, nanoparticles, polymer, and other organic material. Another group that works on the assembly and transfer. Okay. Third group works on the products. What are the applications? The fourth group works on the environmental health and safety, the life cycle of the product. We look at the product from the time you get the nanoparticles and how much energy you consume when making the nanoparticle, and then it goes into how do you assemble it, and then go into the product, and then goes into when it ends up, you know, being disposed of. And so the whole life cycle and the cost of the life cycle has to be looked at. But if I may go back to just making the template, because I talked about one problem, but there's another problem that may be interesting for design, from a design point of issue. So when I give this presentation, a lot of people said, well, gee, so you took a template, you put nanowires on it, and you print it. So that's so simple. There's nothing to it. That's not innovative. And then they say, well, how come nobody else did it before you? And I said, well, because I didn't tell you the whole story. So when we first started this, about 6 years ago, started with the template. So we take the template, which what most people will do, and people have done that before, and you have a surface, silicon surface, and then you make the wires on top of it. So how do you make the wires? You deposit the conductor, for example. It could be gold, it could be tungsten, it could be nickel, whatever it is. You deposit it, film, continuous film, and then you pattern the film. You put photoresist, and then you expose your pattern, and then you etch away. And so now you have a surface with wires. These wires could stick on top by about maybe 100 nanometer or so, okay? And this makes the template. And so these wires are three-dimensional, right? So like that. And then also they're sitting on a silicon oxide, which is insulator. So you have an insulating substrate, and then you have a conductor. And then we tied the assembly with it. And so assembly worked very well until you go down to 2 micron. And then it did not work. So why didn't it work? Well, when you make your wires smaller and smaller and smaller, you go from 2 micron, 100 micron, and then you go to 100 nanometer, 20 nanometers. The resistance in the wire is so high that you would barely get any charge on the wires to attract any particles. And somebody said, well, why don't you yank the voltage? Well, if you yank the voltage, the wire will melt, okay? And so it is like a fuse wire, you know? So it didn't work. That's one problem. The second problem, using this very intuitive approach to it, second problem is that now I have three-dimensional wires. So now the assembly not only happened at the top of the wire, but also happened on the sides too. And I don't want that, you know? And the third problem is that when I do the transfer, I apply pressure and heat, and these wires are very fragile, and so when I do it, the wires come off. So we said, how can we solve all these problems? Well, the first problem is I have to have the same charge everywhere on these wires. So we looked at it and we said, well, you know, the only way to do this is to connect all the wires underneath with a film, which worked. And so now we have a film underneath, and then we etch the structure on the film, and then we coat it with a conductor, polish back, and then I solve all three problems with the solution to the first problem. So now I have even if I have 20 nanometer wire, it has the same electrostatic charge as a millimeter wire, far, you know, nearby or far away. So it's very, very good. Assembly is very good. Second, now all these wires are embedded. there's nothing above, so it's all flush.
So there's no sides.
Yeah. So because they're flush, they don't come off. So all three problems are solved, and that's a problem that you run into, and the student would come in and says, well, this problem will never work, you know. I don't get any assembly. I get assembly on the large stuff. If I do the transfer, the stuff is damaged. What can we do? So, well, go back, see what the problem is. Let's solve it one at a time. And then, you know, and then once you have the solution, then actually the implementation of the solution in the manufacturing is actually very difficult, because we end up using very unique manufacturing steps actually to make the template. So anyway, I just thought to bring that up, because a lot of you say, well, there's nothing innovative about this. It's so simple. How come it's, you know?
Actually, you know what? I don't think they're saying that. My sneaking suspicion is they're not saying that this is so unbelievably simple. I already did this in high school. I don't think they're saying that at all. This is an unbelievably impressive and complex enterprise. I do want to ask you, if, you know, when we spoke, I told you that we had Jerry Hajar as our guest last time, and we joked at the beginning that I said I wasn't aware that engineers empathized at all. And he quickly corrected me and said, no, actually, you know, I didn't think of a structural engineer as being someone who was employing empathy necessarily. But that's, you know, he quickly assured me that that wasn't true at all. In fact, that there are differences, for example, in how people and structural engineers, or the structural behavior of tall buildings, deal with movement in tall buildings. In other words, it might be completely fine structurally for a tall building to move quite a bit, but it would be completely unacceptable for you as a resident of the 95th floor when you're trying to sleep to have the bed moving that much. So are there, I realize you've said that, for example, in your complex organization of people and researchers, you have a whole kind of ethical or human consequences component. How does that, you know, putting aside that, of course, we don't want to have micro particles of poison floating around poisoning us, but do you guys ever zoom out? I know you're so involved with this at a manufacturing scale. Do you zoom out and have conversations about what are there larger problems that we could be solving that we're not seeing because we're down in the weeds here? Is there?
That's true. That's true. Yeah, and some engineers see that and some don't. But that's why we have people from philosophy and from economics involved in the center that actually always try to get us back to the big picture. You know, because the impact of this, you know, could be. I mean, we talked about the specific things that consumers use, but actually, it's huge, because if you think about poor, you know, villages in the remote areas of the world, you know, if I can give them energy harvesting that works around the clock, for example. And I can give him an MRI that you roll in like a poster, and then you the person and put him on top of that and have a full scan, full diagnostics, for example, which is possible, by the way. I mean, and it's all very affordable, very cheap. You know, that will change everything. That you know, we take a lot of things for. I mean, phones became ubiquitous. You know, I tell my students, and I'm going to reveal my age now. When I was in college, there was no laptops, there was no cell phones, there was no desktops. Actually, when I was a freshman and a junior, there was no calculators either. They didn't come out yet, you know. So we had to use something called slide rule. And now we take all these things for granted. But actually, it's 10 years from now, 20 years from now, there will be more things that we'll take for granted, because life is going to become much more easier. The problems we deal in today, you know, is going to be very, very easy. Things that you go to the doctor now to know about your health situation, you don't have to do that anymore. You know, just like the Band-Aid or something in your tears, you can take your tears, put them in the iPhone, and look, and it's complete diagnostics. It even tells you, you know. And I think that in the future, probably send an email to your doctor, and your doctor will prescribe it right away and collect a fee, of course, you know. So it's the future, actually. I mean, for me, my lifespan, I've seen going from a wooden slide rule to do calculations to a calculator, to a desktop, to a laptop, to all that stuff. It's huge. But for you, it's going to be even bigger, because actually the progression and the technology is moving even faster now. than it was back then. Back then it was moving very, very slow.
You know, we're working in the School of Architecture. We're working with CVS, the drugstore chain, and a big global design firm on innovations in healthcare from a built environment standpoint. But it intersects enormously with what you're talking about, because it's impossible now to isolate the kind of, as we know at the university, a single discipline, because we're just saying chemistry, engineering, but also economics and all the rest. I want to focus, I guess what I'm getting at is I want to focus on the issue of how this sort of nano-manufacturing is going to impact health, because it does seem to be perhaps its most dramatic influence, because it interacts with us so intimately in a way that doesn't happen really at all now. The idea that you would consume things that previously had been either injected into you or through other kinds of treatments. Maybe just without going into the manufacturing level of it, but let's just talk a little bit about, certainly like the glucose thing is incredibly cool, because that's very invasive, or the cancer screen.
Okay. So a lot of, cancer is a pretty nasty disease, and for some patients, like liver cancer and pancreatic cancer, patients die within a year from discovering the disease. And my students who started the company, they went to talk to about 50 different doctors, and a lot of them in Boston here. And there's something called CyberKnife. CyberKnife means surgery, cancer surgery, but it's cancer surgery that can be performed in your street clothes. You don't have to take anything off. You can lay on the table with your shirt and everything, and you don't have to wear anything, you don't have to do anything. And the way it works is that they take a radiation beam and they use imaging to focus it exactly on the tumor. And they just apply the beam exactly on the tumor. This was actually, I used to work for Lawrence Livermore National Labs in Livermore, California, and actually that's what the technology was developed in the mid-90s. And now it's available. And so we talked to the doctor, and he said, I use imaging so that the imaging is limited. So if something is much smaller than a millimeter, they can't really see it. And so they see the tumor and they zap it, and they know they zapped it. And then they say, okay, they repeat the process a few times, and the process takes about 10 minutes. And then they send the patient home, and he said, well, I never know if I got all the cancer or not. So I have to ask the patient to come back in 3 to 6 months to find out if there was still cancer left. And we said, well, why? Why do you have to wait? What's the point? Why can't you do it now? Well, because the technology now does not have the low detection limit that can detect very small, minute indication of the proteins, the antigen that the tumor actually produces. It's way, way below. So the detection limit right now is about 3,000 picogram per milliliter. Okay? And you need to go down to about 15 to 20 picogram. So you need to go down by a factor of at least 200, down. And so when the students talked to him, they said, oh, we can go that far. He says, oh, great. That means I can do the test within 1 hour and find out if I got anything or not. We don't have, so what they do now is they wait for the cancer cells to actually grow and become back, so they produce more antigens so they can be detected.
Oh my gosh.
So imagine, and even for people who have family history of cancer, for example, they can go through that. And this is something like a glucose detection. So you take a very tiny blood, put it on it, put it in your phone or put it in the reader, and you find out what the concentration is of these antigens. These proteins are produced by the cancer tumor, if there is a cancer tumor in the body.
Wow, that's really impressive, especially when thinking about those cancers that are so lethal.
And we talked to a liver cancer, and he said that liver cancer is a huge problem for a lot of people who have hepatitis B or C, for example. A lot of them end up developing liver cancer, a lot of them. And in some countries in Asia, because of, I'm not sure what the original cause is, but there's a huge number of population, 10 to 15%, that have hepatitis. And anybody who has hepatitis B or C have to be screened for liver cancer every 6 months. And he said that if I can see them when the when the cancer just started, he said, I can cure them, but not after it spreads in the body. So it's very crucial, you know. So this is actually will increase the survivability by finding things early on, and also for people who had surgery by stopping the, you know, the in remission, you know, to have something caught before it's too late.
Right. Well, I mean, it's amazing to think that we have to. That this is going to be such a dramatic change from what we do right now, which is wait till you're practically on death's door in order to detect. Now, am I right that right now, for example, if you get radiation therapy, it's nowhere near as targeted, and that's why people get.
That's right.
It actually makes you very sick in other ways, and
true,
you lose your hair and all the rest. In your case, which would be a catastrophe, in mine, not as much of one.
Yeah. So basically, for just a note about that, there is a new cancer therapy that's based on nanoparticles. So I can explain how that works, although we don't deal with that. This is just going to your point where the therapy they use, for example, the radioactive pills they use and so forth, excuse me, attacks all the cells in the body. And that's a problem because the body becomes very weak. And a lot of the people that actually are on cancer, on chemotherapy, sometimes die from infection like a flu or cold infection, because the body is so weak to fight. And so the CyberKnife was one of them, but that's really a surgery. It's not something that you take. And so there's a technology that came out in the U.S. and Europe at the same time. And it's now in testing. And so what they do, they take 10 nanometer. Remember, so those of you who do not know the scale we're talking about here, a hair. If you take your hair. A hair is between 30,000 to 70,000 nanometer in diameter. Okay? So the particles that they use for therapy is about 10 nanometer, and they're basically hematite particles, which means iron oxide. And they functionalize those with antibodies that make them stick only to the tumor. Okay? And they inject them in the tumor and around the tumor. And then what they do is they apply a magnetic field, like an MRI. And so this magnetic field heats the particles, they vibrate and heat it. And they heat it by only 10 degrees to 15 degrees. And this is enough to kill the tumor. And there's no radiation involved. And the process takes about 10 minutes. And so it's an injection, and they don't have to actually change clothes or anything, because it's just an injection, and you go through the MRI, and then you go home. So there's and this has been tested. This is in trial testing in Europe right now. If you want to look it up online, the company is called MagForce, means magnetic force, MAG force, and it's a German company. So if you're interested, you can look it up. They have videos and online and so forth. But it's based on nanoparticles, and nanoparticles that are functionalized to stick only to the cancerous cells. So there's technologies, but it's going to take a while. But there's a lot of technologies that does not depend on radiation, for example.
That's incredible. You know, it's also interesting at the intersection between that kind of thing and the built environment is where, you know, some of these services, if they're sort of the most, let's say, transparent or straightforward, you can do them at your own home. You can do them yourself. You can put the Band-Aid on yourself, and the diagnosis goes to your doctor. Nevertheless, there will still be reasons why you have to interact directly with a physician or some kind of healthcare worker, and you know, this is where these worlds, our world of the full-size world and your world of the nano world intersect at places where this is going to happen on a retail kind of basis, because at least I think that is the it's an interim step. I mean, who knows where this nanomedicine will take us in terms of healthcare in 25 years or 50 years, but in the meantime, as we go from this incredibly centralized enterprise where you go to the hospital for a large number of procedures, most of which in the near future you will not need to have done in the hospital. So it's going to change the built environment a great deal as well.
Change your life. I mean, who wants to go to the hospital? Nobody wants to go to the hospital, you know. Even to visit someone, you know, it's a very scary place, and it's a very cold place and so forth, but sometimes you have to, you know. And so if you can do a lot of that stuff at home, or in your office and send the information, that will make it very, very easy, for a lot of people to do it. Make it easy for the doctors, as long as the doctors make money out of it. My son is a doctor, he's a physician, so we always talk about this, and as long as they can make money out of it, they can do that, because basically what do they do when you go to see a doctor? They check, depending on what they listen to you and so forth. You can put your phone on next to your chest and breathe. He can get that. And usually what they usually do is they just ask you lots of questions, right? And if you go to if you've been to CVS, what they call it, the
Minute Clinic.
Minute Clinic.
Yeah.
For example, what happens? The RN sits at her computer and asks you a question, and then she types the answers in, right? And then hits return, and then it comes up with like 4 different things, and then I have to ask more questions to narrow it down to one, and say, oh, that's what you have. You have this and this. I'm going to give you a medicine for that. So doctors usually don't use a computer because they have to learn all that stuff, and they have to go through that in their head. But there is no reason to do that. It can be done. You still need a doctor because maybe the program got it wrong, or maybe one answer could lead to 2 or 3 different things. You still need a trained physician or a trained health worker to help you. But a lot of the easy stuff that you have to go stand in line and wait for an hour or 2 hours sometimes, there's no need to do that.
Right. Well, of course, it's not just from the patient's experience. Who else doesn't want you going to the hospital is the insurance company.
That's right. Yeah.
And as in the research we've done, it's incredible how much they assume that they will be able to reduce the amount of hospital visits dramatically. If you read the newspapers or online, of course, the last several years have been obsessed with the cost of health care, understandably. Yeah. But this is the kind of thing that is actually going to address healthcare costs, is a scalable solutions, not only the little incremental ones, but the ones that change completely how we deliver services.
I mean, all these diagnostics are hugely expensive. All the CAT scans and MRIs, and those are very, very expensive. And the machines are very expensive, huge. In the future, they don't have to do any of that. You may have to go to the hospital, but they put like a blanket, like a plastic blanket on you. And that's it. That's all you need. It will give you the same answer, for example. And that means you can actually carry, a doctor can go in a village and actually set up their clinic and just with a table like this, for example.
Yeah. Well, that obviously, I actually have a friend who's in Africa right now dealing with not the Ebola situation, but another health issue where the lack of availability of resources is just dominant, and I think this is the sort of thing that's going to probably help us out. I'd like the students to be thinking about questions they might have for Dr. Busnaina, but before we get to that, and also don't forget, you can send them to the Twitter hashtag #UnderstandingDesign, and we'll have one of the TAs read them if you'd rather not come up to the mic. But I wanted to, finish our work through the cycle of empathy, clearly defining the problem. We had a long conversation about that with respect to the printing process. Ideation, when you guys, let's say you've already divided the whole nano manufacturing thing into these 4 general quadrants. And when you guys are thinking about how to solve a problem, how do you, in your own group, the one that you work in most directly, I assume that in addition, that you have your own slice of it that you work in directly, do you solicit ideas from your colleagues and graduate students, or do you try to come up with them and have them test them, or how does that work?
No, I mean, we always, in these situations, it's always bottom up. I have my own ideas, but I don't like to share them because I don't want to, bias, the input. And but the ideas, I mean, a lot. We went. By the way, our center had a lot of ideation workshops. We got facilitator from outside.
Oh, really?
Yeah, up to 3 facilitators. We had like 100 people involved. We had companies, and the ideation. The goal was to come up with products.
Right.
But the ideation doesn't really work very well unless unless you clearly define the problem. And most people think that just throwing answers would work. No, it doesn't work.
Right.
Yeah, throwing ideas doesn't work unless you know exactly what the problem is. And so if you don't know what the problem is, you should work on defining what the problem is first before you go into a solution.
Let's pause here for a moment and redouble what Dr. Busnaina just said. Critical. You have to understand the problem no matter what it is, whether it's architecture or whatever field you all are in. These are mostly engineers, by the way. So
if you don't understand the problem, there's no way you're going to come up with a solution, by just throwing ideas at it, And so once you understand the problem, you say, well, okay, well, I understand it, so maybe this will work. Okay, that's one option. Or maybe if we do it this way, and somebody says, well, no, this will not work because of that. Well, maybe we can fix it so that we can get what we want instead of doing that. And so the ideation workshop I went through with the exercise is not really productive because they say, just any idea. Well, we went through about 4 workshops. Really, you get junk out of it, And so we really try to focus a little bit more, and the ideation workshops also don't want to discuss technology. Don't want to discuss details, and that's actually not good if you're looking for a technological solution or a product. And so the way I do it is basically we have what the problem is, and I ask my students and my postdocs, well, what do you think the problem is? Is this and this, and some of them are very outgoing, and some of them are not, and so I have to go one by one. Okay, you tell me, what do you think the problem is? You tell me what the possible solution. You, and then I go through all of them, and then we summarize them, and then I tell them what I think, and then sometimes some of them will come up with my idea. Oh, that's fine with me, I don't, it doesn't bother me, but sometimes they don't come up with a solution, and then I say, instead of telling them my idea, I say, well, why do you think these ideas will not work? Well, we go through them and say, well, what do you think would work? How about if we use this? Give them part of my idea and try to lead them to the idea that I think would work. My idea, sometimes I do that, sometimes we try it and it doesn't work. Well, not all ideas work, There's no shame in that. But if you say, oh, this problem's so hard, there's no solution, it's, I had one of my students, for example, this is many years ago. She's a vice president of a huge company now. And we're working on a problem, and she was doing the experiments, and the data comes in. She's looking at particles, and she's coding them and studying how very small particles actually deform because of molecular forces. And she put the samples in the chamber to coat them, because at that time, the scanning electron microscopes have to be coated with gold because there's a lot of charging for polymer particles and so forth. And so every time she puts it in, she finds out that sometimes it was good, sometimes it's deformed, sometimes it's half deformed, and on the same sample, same conditions. I'm saying, and she worked for 3 months. She couldn't work. She gave up. She said, this problem's so hard. Maybe that's why nobody looked at this problem before. I said, wrong. There is something wrong going on with your experiment that you have to find out, and you have to go back and think about exactly where you do this, how do you put it, where you put it in the chamber, and so forth. And then I started doing research into the process, and the process is a physical vapor deposition, which means that there is a magnet up there that applies plasma and sputters gold, for example. And if you look at the cylindrical chamber, the magnet has higher temperature at the center and lower temperature at the end. So what happens, the samples she puts at the edge are only deformed because of molecular force, which is small deformation. The samples she puts in the center deform a lot more and becomes like a hemisphere because of the heat. And then once we did that, she puts all her samples at the edge, and that. But 3 months looking for the problem, and then she gave up. And I'm saying, no, this is a problem that you can find a solution. Every problem has a cause, and if you can define the cause, you can find a solution.
One more thing I wanted to ask you about I guess you'd say it falls into the prototyping category, and that is the concept we've heard about in different contexts of fast fail. And I wonder how that applies to what you do, because it would seem to me you'd love to find the errors as soon as you could.
Yes.
So how does that work in your?
It's very difficult because you make the stuff and you can't really see if it worked or not, because it's very small, and not even an optical microscope will not help you. Even if you have a magnification of 2000x, it will not help you. You have to go to 100,000 magnification to actually see if the process worked. So it's very, very difficult, and sometimes we design some circuit to see if the process worked by just measuring if there's conductance through it. So And you know what? In most of these things, it's so difficult, and there are so many parameters you have to control to make this work, that 90% of the time, when you first try the second, third, fourth time, you will fail.
Right, right.
You know, and it's really very precise control of the process. I mean, the one estimation I showed you is very simple, but if you try to do it, it'll probably take you a year to come up with the process parameters that we actually use. Okay. So it's very, very difficult. It's not like, you know, you make something and then you see, oh, okay, that works. You know, I can see everything connected. Or I can plug it in, works. It doesn't work like that.
So
it's very, very hard.
So it's harder to, I guess the fast-fail concept, if you will, comes really from the software world, where they want to write a bit of code and test it right away, rather than write the whole program and find out later that it had flaws that were detectable early. Maybe that analogy is not really working here.
I actually used to write software, and I used to write the whole thing myself, and I had a business out of it.
Right.
And I know how that works, because in the old days, when people wrote programs in the 60s and 70s, and believe it or not, people wrote software in the 60s and 70s, although it was not for phones or computer or laptop or desktop, but for mainframes. You know, and they use same language you use today, C and Fortran and all that. And at that time, the non-professional used to write one big source code. Okay, and in one big source code, if everything fails, you have to go through the whole thing. And you have to put like print statements between each line to find out exactly where the problem is. You know, and so, but in the 70s, people moved into subroutines. And subroutines, each subroutine does a specific function, for example. And you can teach these subroutines separately.
It's like modules.
That's right, modules, yeah. And then the whole thing got subroutines, and the main source code was really just an instruction to subroutines back and forth, you know. And so that made it much easier and much more easy to debug, and much more easier to avoid the failure, the big failure that usually you run into.
And I guess the question is there an analogy between that compartmentalization and what you do?
There is an analogy, because you really have to, so when you make a product, for example, you have the conductors, you have the semiconductors, you have the antenna, you have all that stuff. And so you have to test each one of these separately before you put them together. You know, you have to, even in the phones that you have today, for example, a processor that, you know, in the iPhone now they use, and in the MacBook they use Intel now, because they used to use Motorola, for example, chips. And with these chips, for example, you know, you can have up to, so it's a circuit. So you know, when you see a printed circuit board, right, in your computer, you open the computer, you see this green thing with all the wires. Well, the chip is actually exactly the same, except it's much smaller, and it's actually, instead of the polymer, the green polymer you see, it's actually silicon. And it's the same thing. It has many layers of circuit. And these layers of circuits are interconnected. And so the semiconductor industry, when they change the interconnect material from aluminum to tungsten to copper now. And they may go to nanotubes. So every time they change it, or they change the process, or they change the dimension, they have to test these things separately before they put them in the system, because they have to make sure. They have to make sure that they're insulated. They have to make sure there is no migration of electrons through the insulator that surrounds them, for example. They have to make sure that they get enough signal between the bottom layer and the top layer, for example. They have a global interconnect. They have local interconnect, for example, which are smaller, and then larger ones. So these things have to go through a lot of testing before they even go to the product. You know, before you introduce it into the existing manufacturing process, you better actually do it very carefully and repeat it, and it has to be reproducible, repeatable, and it has to be within a very narrow window of performance, for example. So it's very, very similar, you know.
It seems to me very important, and it's one of those lessons that is applicable across disciplines, this idea of trying to fail quickly and to compartmentalize things so that they can be understood more legibly. When we get to the portion of this course where we're going to talk about a whole nother field altogether called experience design, we're going to be breaking apart experiences that people think of, most of the people in this room think of as being all part of one big undifferentiated thing. But in a very surprisingly scientific way, we are going to chop this stuff up into little bits and be able to analyze each part. With that, are there any questions from the audience?
So why isn't the 3D printing of electronics widely adopted? Do you see resistance from companies making billions from the old technology? And when do you think nanotechnology will become integrated into the lifestyle of the everyday consumer?
Very good question. So basically, the 3D printing is, as people talk about it, is really for making parts. Okay, not parts that have circuitry inside or something like that. That's done mostly on the 2D printing. But remember, 3D printing is basically 2D printing stacked up. That's what it is. They do one layer at a time. So for example, I saw, I'm just explaining the 3D printer. So now GE and Pratt & Whitney make turbine blades out for 3D printing. And most people say, well, those of you who know material science say, well, how could they do that? This is basically ink that has these particles, and they put the particles on top of each other. How they can fuse them together? Well, I can tell you how. Each layer, they have a laser that melts all the particles in that layer completely. So they become one film, and then they put the other one, and then they put their laser. So it's really very, and so 3D printing got all the publicity, but electronic printing has been around for a while. And just kept up because people looked at it as a cheaper way to do things besides doing electronics. But also they had a strong need for flexible circuits. You know, that you can wrap around something, or that you can make it flex and so forth. And doing that with silicon is hard. You know, you can do a flexible circuit with silicon, by the way. It's not easy. Okay, and also the printing was 1/10 of the cost of doing silicon. So, but it has limitations, by the way. Because if you print on polymer, that means you cannot put this circuit or this chip into high temperature environment. Okay?
The way you could with silicon.
That's right. We do with silicon. So it's kept up, and now people are looking at it. And so far, the big companies, Intel and Samsung, have not paid attention yet. But Samsung is paying attention, by the way. Intel has not. And LG also paying a lot of attention, for example. So, and there are some companies like Flextronics, big company that does flexible electronics, but they're not paying attention. Why? Because these companies, they know these companies are working with a technology that is only capable of printing 20,000 nanometer or 30,000 nanometers. And this was the technology for silicon back in 1980 and 1982 and 83. So I say, oh, these guys are so far behind. We're 20, 25 years ahead of them. But guess what? Once this technology we're doing nanoscale printing comes up, then they will pay attention. Okay? So right now they're not paying attention, but actually they will pay attention in a few years from now because this will threaten their business.
So it's the short answer is that it's the tolerances right now are not the same between the two manufacturing systems, and but when they are, the advantages of nano will be so enormous in terms of speed and cost and flexibility and all the rest that it will be impossible to ignore.
Yeah, it's not just tolerance, because for the engineers, tolerance means something completely different.
Oh, okay.
Tolerance means how much I can vary my, if I make something part that's 1 centimeter, tolerance means how much I can, is it plus or minus, you know, certain.
What do I mean then? The scale?
You mean the scale.
Yeah,
the scale.
Yeah, okay.
The scale. So the scale, for example, I worked with IBM back in 1985 to scale their process. And at that time, the smallest dimension they can make is 1,000 nanometers, for example. Now they go down to 20 nanometers, for example. Wow. Okay? So the printing electronics have not even caught up with IBM in 1985. Right, okay? Right. But this technology I talked about will actually let them go not just match what IBM did in 85, but match what Intel does right now.
Right. With all these other advantages.
That's right.
Yeah. All right. Let's have another from the audience. By the way, if you want to get up and ask one at the mic, you're more than welcome to.
What are your thoughts on how your printing method relates to nanotechnologies such as graphene supercapacitors?
I was going to ask that, but since he got to it first.
Well, graphene, for those of you who don't know, so most people know nanotubes, right? How many people know what carbon nanotubes are?
Heard of them.
Very small, yeah. How many know what graphene is?
I've heard of it.
So, okay, so about the same number, okay. So you know what the connection between them is, right? If I take a, can I borrow this? Sure. Yeah, so this is a nanotube, okay? It's carbon atoms that are like a chicken wire fence, you know. And if I open it, and actually, by the way, lots of people know how to do a chemistry just to open it like this, and then make a sheet out of it, you get graphene. So nanotubes are just folded, it's graphene folded into cylinders.
Nice.
Okay, so they both have very similar, I don't need
quality.
Yeah. They have very similar properties, you know, but with one difference. They're both very good conductors. For example, graphene is a thin film. Okay, carbon nanotubes are cylinders, very tiny cylinders. They differ in the sense that with nanotubes, you can get nanotubes that are semiconducting, and you get nanotubes that are conductive. With the graphene, it's a semi-metal, okay? It's conductive. It's not semiconducting. And so to make it semiconducting, they have to put, they have to dope it to make it semiconducting. That means implant something in it, or apply a chemical that reacts with it, and so you have molecules in there that will give it that property. So a lot of people are using it for supercapacitor, but you can also use nanotubes for supercapacitors. The same thing. Supercapacitor is just like a battery, except it's give you a charge very quickly, and you can charge it very quickly, and it's used for a lot of applications. So I think you're going to see. So this is something we didn't talk about. So the product, which product we're going to see first? Mm-hmm. So any energy-related products like supercapacitors, battery, energy harvesting, there's a huge need for that, because there's really totally need for that. Sensors also, medical applications, you're going to see a huge in that. Electronics, are we going to see the companies jump on using electronics material? No, because right now, would it make any difference for you if your processor was twice as fast? Nobody cares. People, some people don't even distinguish, don't even know that flash memories are very slow until they try to store a movie on a flash drive, right? Then you realize, oh wow, this is really slow, you know. And so, but the flash drive is slow, and so people are making, but your DRAM in your computer is very fast, for example. Right. So, but most people don't even notice because we're using it for, you know, for editing and so forth. Right. So there is no huge need from consumers for much higher performance, okay, and much smaller circuits. So the need is not there yet. It may be there because people will make you know, software that will need more memory and so forth. But there is a need for sensors. There is a need for detecting cancer, detecting other diseases faster. There's a need for treating it. There's a need for batteries that will last longer. I mean, we talk about batteries in terms of, you know, phones, right? But think about satellites, okay? Now, how satellites work, okay? Now, when somebody puts a satellite, they spend millions of dollars just to put it up in orbits, okay? Now, this satellite has to stay there for 20, 25 years. Now, it has batteries, mind you, and they have to be charged, okay? Now, you have no chance of changing that battery, you know? And also, it has to be recharged within 30 minutes, fully charged in 30 minutes. Why? Because as the satellite goes around the Earth, it has an exposure to the sun for only 30 minutes at a time.
Really? Huh.
And so when the solar panels are open, you only have 30 minutes to charge your battery. If your battery is not fully charged in 30 minutes, too bad, you know? Right. And so the satellites have to last very long time and have to be fastly, you have to charge it fully within 30 minutes. And you cannot change it. It has to last for 20 years. It has to last 20 years. So there is a huge need for that, not just for satellites, but also for, so the medical need and the energy need are the ones that will actually benefit fully, because people know if they make a better battery, they can sell it. Right. They can make a better energy harvester, they can sell it. If they make a better medicine, better sensor, they can sell it. If I can make a processor that's 10 times faster than the processor you need, you wouldn't even notice.
Right, right. This is one way in which times have really changed. Yeah. But I think on that note, I want to thank you very much, Ahmed. Thank you.